another compiler building stream. So in the last stream, we have implemented more binary operators and even added unary expressions. So we can now say something like -1, and this is a valid expression. So for example, -1 plus 2 would evaluate to 1. Let's see that. And it works. And that is pretty cool. And we also have added some tests. So we can now say cargo tests. And I think we have added about 14 tests, yeah. And so we can now ensure that the code that we've written in the past still works. And we've added tests for both the AST structure and our diagnostics reporting. So we also know that errors that should be reported are reported. And today we will implement if statements. So basic control flow structures, if statements and while loops. And I'd like to talk a little bit about what we have to implement for that, like, and what we have to watch out for. So basically, write down a little checklist maybe. What do we have to consider? So what do we have to consider? So basically, if statements, they have take a condition. So we need kind of a new type. Right now we only have int types, but now we need Boolean types because this expression has to evaluate to a Boolean value, right? And then we have some kind of pieces of code that can be conditionally executed. So right now we only have like one flow in our program. So every statement that we write here just gets executed. So that has to change. So new type Boolean. And we also need conditional executing of statements. And we also have to consider like how we want to handle scoping. Because if I declare a variable in this scope, it should not be accessible outside of the scope. So if I say like that b is equal to 10, b should not be accessible here, right? Because that would make no sense. So we also have to consider scoping. Yeah, we'll think about that. Okay, cool. So I guess let's just get started, right? So first step to adding new constructs to our language is adding them in the parser. Like first of all, we have to lex new keywords, which in this case would be if and else. And what we also have to think about is, do we want if statements to be just statements, or do we want them to be also able to be used as like actual expressions? So you can say something like, okay, like b is equal to an if statement, right? So then you could say like, I don't know, 10 and 2, and then b would be 10 if x was greater than 10, or 0 if not. I mean, for now, I think we'll just implement ifs as pure statements, but later on, I could imagine that we'll be using them also as expressions, because that's a pretty neat feature, I guess. So yeah, let's get started. So we have to lex some new keywords in the lexer. So we have to add them to our token kind enum, to be if and else. And then we have to add display for them, to just be if and else. And then we'll have to lex them in our identifier lexing method, right? Okay. If and else, cool. So now if and else are valid keywords. Let's just write a quick example program of what we want to achieve today. Just say that a is equal to 0 because we don't allow uninitialized variables for now. Then we can say if I don't know, let's say let b equal to 1. We can say if b is greater than a, then we will say a is equal to 10, else b is a is equal to, I don't know, 5. Okay, so that's what we want to achieve. Let's see what happens if we run this now. Nothing good, hopefully. Yeah, okay, so we get a bunch of errors. And we can see that our AST is looking kind of weird. Because everything is basically just parses in a separate statement. Yeah, expected expression for if. That's fine. It's actually good. So now let's get to the interesting part of parsing the if statement. So we'll have to do that at the same place where we parse our let statement. So we can just say when we see else and else, if we want to parse an if statement. So what will our if statement actually look like? That we will have to define in our AST file, where all our expression statements are defined. So we have to add a new statement kind, which will be if statement. And we'll have to define a new struct, AST if statement. So this will hold in probably, I don't know if we want to keep the if keyword in there. For now, I don't think we do. So what we could do, we could say if keyword. I mean, yeah, let's just do it. Why not? And then we could say condition, which will just be an expression. And then we'll have a like then block. So it would just be another statement, I guess, which we'll have to put in a box. Like that. Statement. I guess we can just call it then. And then we'll have, I guess, what we could say like else keyword. Could just be option of token, right? And the same for else. But they kind of belong together, right? So if one of these exists, then both should exist, right? So what I like to do is I like to introduce a new abstract st else statement, which will not actually be a separate statement, but like rather be in the if statement itself. Right, cool. So now we can try to parse this actually. Where are we? I think we kind of have to clean this file up a bit. It's a bit long, for my taste at least. Let's see. We're not in parser. We'll make things a little bit easier. So let's make parse if statement, cool. So parse if statement. We'll just take a mutable reference to self and return an AST statement. So first we have to consume the if token, and just to be safe, we'll use a consume check. It should always be an if token here because we check for it here, but just to be safe. So next up would be like a condition expression, parse expression. I mean, optionally we could also parse like brackets here, I guess. I don't know if we even want brackets like to be a valid syntax. Let's just not do that for now. Like what I mean is you could of course put brackets around here, like in Java or something like that. But I don't know, I don't like that, to be honest. So maybe we'll add that in the future, but not for now. And now we have a condition expression, and now we have to parse a statement, right? So we can say that then is equal to parse statement, because there can be any statement. We don't necessarily need like a block statement which is surrounded by curly braces. There can only also be like we could also leave these out, I guess. That should be valid, right? So And now we have to parse an optional else statement, right? So we can just say parse optional else statement. That's the else statement to wrap around in an option. So we can say if current token is equal to token else, we can parse the else statement. So self consume and match check just for good measure, and we can parse the else statement. Else, which is a return none. Statement new blah blah. Just add a constructor here. You don't like this? Expected token. Else keyword. Okay, so we'll have to keep track of this. Else keyword. And we'll probably have to clone this, right? Yep. Cool, and we'll have to put that inside a box. Yeah, let's just not do that here. Let's do that in constructor itself. That's cool. And now let else statement self parse optional else statement. Yeah, that's correct. And now we can actually construct our if statement. Well, let's just add a constructor for that in our AC statement. Construct and if statement. Okay, cool. That works. And now we can say parse if statement. Where are you? Thank you. And we can just say AC statement, if statement. And we are missing out on the if keyword, so let's just create a variable for that. Oh, okay. That was a bit of a lag here. There. I hope the stream is still running. Seems fine. Good. Okay, that's working. So now we have parse. Okay, makes sense. Now we have parse if statement. Okay, so we're running into issues with exclusive borrows. Let's see if that fixes it. Actually, does it? Okay, cool. Okay, it actually does. Nice. I think we can even remove these mutable references here because they were just here because our consume methods used to take a mutable reference, but I don't think we need these mutable references anymore. I mean, if we'll ever run into problems, we'll remove them, but for now it's fine. Because what the problem was that consume needed a mutable reference because we usually had, first version we had like just a usize here for our position, which was directly stored in the struct, so we had to have a mutable reference to be able to increment the position, and we've replaced that with a struct called a counter, which just wraps the usize or the value in a cell, so we get interior mutability without having to provide a mutable reference, which is kind of nice. So now we're parsing an if statement. That should actually work. Now we'll have to like implement missing cases in our match statements. In our visitor. So statement, and we just say visit if statement. Then visit if statement. We'll take a mutable reference, like all the other visitor methods. And we'll now provide a default implementation for that. So probably also have to add this. No, we don't. In our printer, I guess. Yep. So wait, where are you? No, here you go. So we'll just push an if keyword guess I think we need some utility methods here because that's just duplicated code. So we can just say, I don't know, like add keyword string. Yep. So we can just say self add keyword now. If, and we can also replace this let this new method add keyword let. Okay, cool. I think we're gonna migrate that over time. I mean, we could also just say like push text or something like that, or like add text, add text or something like that. Yeah, add text. It's actually good. So we can, instead of doing that, we can just say self add text and move that back. And I guess we, why you know, like this string. Okay, so as to the rescue here. Cool. We could also replace that, I guess. Yeah. Self text. Okay, cool. Now we'll have to visit our condition, and then we'll visit our statement, right? So the body, then branch. I think we could actually rename that to then branch. That's actually cool. And exactly. So if we have an else branch or else statement, actually, yeah, let's just let's call it else branch just for consistency. And we'll add the keyword else and visit the else branch else statement. Cool. So our code generator should work again. I think we're gonna run into problems with like nested scopes. We'll need indentation then because we want like nested scopes to be indented, but we'll worry about that when we add like block statements. So we also have an AC verifier. That's for our testing. Right. Visit statement and visit statement. Okay. So like if, and we'll have to push probably else here. So we'll have to add an if else here. Okay, nice. So can we run this now? No, we can't. Okay, we have to add support for that in our evaluator, which is actually, yeah, for now, I don't even know if we need Boolean values. I mean, we can just do, for now, like we store integers here in our last value. We can just store 0, 1, like 1 for true and 0 for false. That would work, I guess. So we can just say like let if I have to visit our condition. Yeah, exactly. If our last value was not 0, then we just visit our then statement, then branch. Otherwise we like either we do nothing. Would that be fine? I guess it'll be fine. Like and if let else branch we'll visit the else statement. Yeah. So this code is not gonna work because we're not parsing these curly braces for now. We also have to batch. Okay. I think we could actually provide a default implementation because this is kind of code duplication all over the place. I guess it's fine for now. And we have to make these public as well. Yeah, and these properties also have to be public. Cool. Okay. Wait, is our build still running, or are we running into infinite loops? What? Okay. That build took much too long. Okay. So for now we don't have any relational operators, so that's not good. So I think first of all we should probably introduce block statements, or maybe not. Let's just remove these for now, and let's try to lex this relational operator here. So we can just go into our lexer and say lex punctuation greater than token, no. Greater than, I guess. Greater than. So we'll just have support. Let's just do them all. Less than, greater than equals, less than equals, equals, not equals. Sure. Why not? Why not do them all? Okay, so now we're running into the same problem as with our power operator, where we have to match next char. Yeah, so let's think how we can generalize this logic. I mean, I guess, say, Fn like lacks potential like double char operator. Okay, that's a pretty bad name, I suppose. One char kind, token kind, double char kind, token kind. So if do we need that? We don't. So let's say exactly if next is equal to okay, we have to add this back next char. Next expected to yep, okay, cool. So we can just say double expected s squares double s squared. Nice. Okay, so we can do the same for greater than, right? Yep. And the same for less than. I guess we're not supported that for now. So we're relaxing all of these now, like less than equals. Yeah, looks good, looks good. Alright, do we relax equals? No, we don't. Okay, so we have to add these to our display. Execute a copilot. Okay, so we're parsing these, and now we have to add them to our binary operators. Binary operator, binary expression, operator, operator kind. So we'll have like arithmetic bitwise, that's not quite correct. And we'll have like relational. So like equals, not equals, less than or equal, greater than or equal. Okay. So now let's see. They'll have a greater precedence than all the other. It's like not too much sense, I guess. No, like 21. I don't even know. I'll just ask ChatGPT once again. Can you tell me the precedences of relational binary operators? Why is my stream not running correctly? That's pretty weird. What? What? I don't like this. What? I think I'll have to fix that. Wait, what? Okay, that's annoying. Let me just remove the scene and add it back in. Okay, now you're just in an infinite loop here, I guess. Okay, now it's working. Okay, that's pretty annoying. Okay, sorry for that. Okay, so not equals and equal to are have like the highest precedence, I guess. So they'll just get 30, like 29. Sure, 29. So now we have precedence for our binary operators. Now we'll also have to parse them correctly. So like parse binary operator. Just have to say like token and equals bang equals less than equals greater than equals. Okay, less than or equal, let's call it here, and greater than or equal. Cool. So now we have this in place. And I mean, I think nothing's stopping us now except for our evaluator, probably. Yep. So I mean, we can just say if yeah, let's create a helper method for that, like eval boolean instruction. I don't like self like instruction. Wait, how do you even use functions as parameters in Rust? We should have never done that. Wait, is Okay, just something like what? Fn. Yeah, of course it's Fn. Okay. And you'll return a boolean, right? Okay. What is happening here? That's not quite correct. Oh, so we'll have to move that to a different implementation block, I guess. Oh, okay, that's not valid syntax. Like dynamic. So let's see. Oh, like let me just check like some random iterator method help. Oh, my mouse just ran out of battery, I guess. Let me pack that in real quick. Cool. So now we're back. We just do that back new iter like map. So how is that defined? F where fn mu self item. Okay, so you define it like that. Okay, that's actually interesting. So you say like instructions f like f where f wait. Okay, that's kind of rough. Check that out. To try, okay, for return time first, where, okay, where fn mute, okay, where fn once, I36, I36, cool, okay, cool. I think we need that, right? Okay, so now we can just say self.eval instruction. Cool, that should work. So now if we run this, what is actually expected output? Expected output would be, if we add an A here, would be 10, right? Please. Okay. Expected expression found. Okay. That's actually weird because this should actually work. If this is parsed as a binary expression, and so is this. Not binary expression. Wait, do we not have assignments? Oh my god, I think we do not have assignments, right? So we do not have assignment statements. Yeah. Okay. I guess that makes sense then. So for this to work, we'll have to add assignment statements first. Or expressions. I think we'll even implement it as an expression, so you can say something like a is equal to 10, right? Like this. Which would return 10 in this case. I don't know. Will we do that? Does that make sense? I think it actually does, right? Does it? Yeah. Yeah, that's implemented as an expression. I think that's the way to go, to be honest. So, essentially an assignment expression is just a binary expression. Yeah, basically. But like you have no precedence stuff and so on. I mean, for now it's pretty simple actually, because the only thing that can be assigned is just plain variables. So when trying to parse an expression, we can just check, okay, do we have an identifier token here? And if yes, is the next token an equals? And if yes, then we'll try to parse an assignment expression. So let's first add our new node here, like expression kind, assignment. Nice, the assignment expression. Struct ast assignment expression, which would hold an identifier token, and an expression. Like we'll just call it not initializer, expression. That's okay. Yep, do this statement. So visit assignment expression. So visit assignment expression. So if we're already here, we can also implement the default implementation for if statement. Yep, that's correct. Cool. So we've duplicated code completion. Okay, so we can just remove that, I guess. Nice. Okay, so we'll need an visit assignment expression. Cool. And we'll have to parse that somewhere. Parse expression, or parser. Parse expression. Statement, parse expression. And before trying to parse a binary expression, we should parse an assignment expression. So fn parse assignment expression, which will just return the expression. And we can also implement the new constructor here, like assignment identifier token. Cool. Parse, oh, once again, wrong file. So we can just check if that's current equals, I mean, we could probably even better with like match. fetch self current, I guess. Oh, probably need self as an argument here. Now let's just say if self current kind token kind identifier, we'll say and if that's token, if that's equals, wait, does that work? Okay, it would actually be crazy. That actually works. Okay. Cannot borrow. Okay, we have to borrow use mutable. Peak one. Okay, that's fine. Cool. So now we're checking if our current token is an identifier, and if the next token is equals, then we'll try to parse an assignment expression. Yeah. So yeah, it actually looks kind of dumb, to be honest. Okay. Yeah. Wait, is there, what is our visit assignment? Where's a visitor? Visit assignment expression. You do anything? Okay. I guess, do we want a default implementation here? Yeah, maybe. Okay. So we have to specify that in our printer first. So I guess visit assignment expression. Just say, yeah, and add variable, I guess. Add variable, which will just be literal of the identifier. And then white space, text, white space, yep. And now we should get better formatting, right? Yeah. We also need white space after the condition in our if statement, I guess. White space, white space. Nice one. Okay. So this looks a little better, I suppose. Right? Yeah. And A is 0, which means that none of these statements were executed. I mean, they probably were, but our evaluator doesn't implement them. So visit assignment expression, let identifier, yep. So we'll visit the expression and insert assignment. Okay. Yeah. It should work. Let's see. Nice. It actually is 10 because B is greater than A. And let's say B is -1. Now A is 5. Cool. So these statements are working. So next step would probably be to enable a multiple statements to be executed. So, I mean, right now, what would happen is that this would not work, right? So, blah, blah, blah. Hello. Yeah, okay, sometimes GitHub Copilot is a bit annoying, I suppose. Because that does not work right. We just get an unexpected token stuff error. Yeah. So what you typically do is you add another kind of node in your to your AST, which is called like a block statement. So a block statement essentially is just, yeah, as the name says, a statement which is which begins with an open brace and ends with a close brace. So this is then also where we'll get into the concept of scopes, because every time you enter a block statement, you're in a new scope. Yeah, so we'll do that afterwards. But first of all, we have to parse that. So in our AST file, we'll have to add a new statement count block statement. I mean, we could probably also rename those, like to let and if and block. Abstract AST block statements. So, and this statement will just have a bunch of statements. Cool. And the corresponding visitor method and visit block statement. Yeah, nice one. So next step would be to parse this somehow. So we'll just say parse statement, and we'll probably need another new token kind, yeah, like open brace parse block statement. If parse block statements, yep, close brace token, statement consumer check, close brace block statement. Yeah, that looks good. Block statement. So block statement just takes a vector of statements. Does not take open and close brace, at least for now. We need that. And we'll have like open brace, close brace. We'll have to implement display for them. What's that? Oh, wait. Rust doesn't like that? Okay, that's interesting. I did not know that. Okay. They could have Copilot, I guess. Because of formatting stuff, right? Yeah, because how the format makers work. And we do not want to do that. What? Thank you. So now we're parsing these, so it should work now. Cool, so we get some errors. Why is that? Okay, we don't actually. Wait, okay, it's already working. Cool. So should our B should be 2 now, right? Very nice. So it's actually working. Something is weird with the indentation here, I guess. Yeah, let's fix our output of the AC because that just looks ugly. AC printer, where are you? Cool. So we do not need a white space. Wait, a white space before our else keyword, I guess. Do we? Nope. But we'll have to indent here, right? So I don't know if we have indentation. Yeah, okay, we do. So we can just say like fn at padding. Yep. Okay. Yeah, okay, that's fine. So we're gonna do that before we visit any statement, right? So we just say self add padding, and when we enter a visit block statement, a keyword now, we'll add self add text. It does not work, right? Okay, it does here. Weird. Oh, because we were in the right macro. Okay, that makes sense. Why do we padding here? We don't. Okay, maybe. Yeah, okay, maybe we do. So, okay, cool. You see that? That works. Now we pre-print again. And else, we'll just execute this thing. Cool stuff. I like it. So now, let's get to scoping. So scoping is going to be interesting, because the problem right now is something like this. So we just go in here and say like let C is equal to 10, and then we'll try to reference C. It will not throw an error, right? As long as B is greater than A, because then this will be executed and C will be assigned. So see that? Right? So 10. But if now B is -1, we will get an error. Yeah, because now C is not assigned. So we don't have a value for C at this point. So to fix this, what we have to do is add scoping. So what we currently are doing is we have something like a symbol checker. I mean, the name is not perfect, but we'll just leave it for now. Could actually rename it to something like resolver. Yeah, let's rename it to resolver. Resolver. So our resolver just walks the AST and checks if variables are accessible, where they are accessed. So right now our symbols is just say flat like hash map list, but what we have to do is we have to add like a stack structure, because a stack is perfectly suited for this use case, because every time we enter a new scope we just push something new in the stack, and when we exit the scope we pop the scope. I mean, as simple as that. So to make our life a little easier, we're just going to introduce a new struct called scopes, which will hold a list of scope. So just have symbols, and this will just have scopes. And our scope method or scope struct will have like a method to insert and to read symbols or look up symbols. I declare, right? And look up. Yeah. And our scopes struct will like also have these methods. Like we can just say like enter new scope, enter scope, and exit scope. And declare will declare in the latest in the scope on top, because that's what we want. Like if we declare a variable, we only want to have this be accessible in this scope. And essentially in the lookup, we're doing the top-down lookup. So we start at the topmost scope and try to find the current the identifier that's being looked for. And if we find it, that's cool. We just return true. If not, then we'll just try to find it in the next scope. And if we don't find it there, then in the next, and so on, until we are out of scopes, and then it's just not found. So, like scopes new. Self scopes declare identifier if self scopes look up so if we do not find anything, then we'll report an error. And this is actually pretty simple, because what we can say is like, so when we visit a block statement, we just enter new scope, and voila, that's it. Now we should get an error, right? Oh, I can please terminal. Okay, weird. Wait, what? And we don't. That's embarrassing, I suppose. Why? What? Should not happen. Wait, how is this even working? It shouldn't even be working in any way, because the problem that we have is that our scopes is just empty, right? Because we have to push an initial scope. So how does this even work? So if we look up, we iterate overall, and if any takes a closure, if they all return false, it returns false. That's what we want, yeah. Empty iterator returns false. Okay, I mean that's fine. This should not work. What? Do we ever get here? Yes, we do. So let's just step into that method. Huh. And that works. Wait. Size 0. Okay. Now what? Wait, was that the arrow before? Oh, it wasn't. Okay. So what we have to do here is we have to say, like, it's gonna be scopes. Before we do anything, we just say, okay, scopes, enter scope. As simple as that, and now it should work, probably. Byte index 2 is out of bounds of B. What? Now we have some issue in our diagnostics printer. Byte index 2 is out of bounds of B. Ah. What? That should not happen. Prefix end is column. What? It's perfectly fine, right? Like, why do you even complain about B? Wait, let me just print diagnostics. Undeclared variable C. Start 9. Okay. I mean, that's correct, right? Like, I don't see the problem here. Byte index 2 is out of bounds of B. What does that even mean? Why is B in here? Something's not right. Let me set a breakpoint here. Okay, line. Why is our line just B? Okay. What? Prefix start, prefix end. Okay, that should not happen. Why is our line B? What? How can our line ever be B? What? The actual, okay. It's interesting. So our line index is 10. And our line is B. For line index is 10, we should take the 11th line. Right? So 1, 2, 3, 4, 6, 7, 8, 9, 10. 11. Yeah, okay, that works. Now I wonder why are you line 10? What? Span is correct, right? Literal C. Start 161. I don't know if that's correct. Do we have how many characters do we have here? Okay, this is formatted, right? Because in the original text there's just a bunch of white space in front of each line. So makes sense, I guess. But just why are you line index 10? What? Line B. No, this is not correct. I think we'll just write a quick regression test for that. So we'll just take this code, go into our tests here, say should report undeclared variable, or should report when variable was declared in another scope. So we'll just have like input like this. Yeah, that's fine. Undeclared variable C. So this should panic as well, right? Please, nice. Yeah, okay. So we reproduce the issue. That's cool. So somehow our line index function does not work very well. So we just say, okay, we take our text, go until this position and take the lines count. Which seems reasonable, to be honest. That seems kind of correct, actually. So which text do we pass to the source text? Input, like the actual input, right? So maybe this does not work as expected. This string slice. Those lines are ended with either a new line or a catch return with a line feed. Okay. Final line ending is optional. A string that ends with a final line ending will return the same lines as an otherwise identical string without a final line ending. Ha. Okay. We could do for testing purposes. Let me just print line the input indexed by 161 to 163. That would not work. Hello, please. So this should print C somewhere, right? C. Okay, this is definitely correct. So now the problem. Wait. Let me think about that. Like the line index. Okay, the problem with the line index actually is that C is like one line below B, right? So I guess line index. Okay, I think the problem is with this here at the beginning. That's actually annoying. So I guess this will just be the count. Like an iterator over the lines of a string. Find an option of string it in the same lines, otherwise okay. Count. So this should always return like start with a 1, right? Because it always has like one line right. So what happens if we do this? Okay, this works. Does this break other things though? It's a question. Yeah, okay, it does. That's actually annoying. So let's see. Should report bad token in our diagnostic tests. Okay, so you break because you're in a single line, right? So what does it return actually? It returns like index. So that's probably called, let's see, it's probably called with a 1, right? Yep, okay. Maybe zero indexing is not that good of an idea, actually. I mean, to be honest, I don't see the problem. Why does this fail? Like, why do you return 10 here? Oh, I see. I think I see the problem. Because this is not inclusive, right? We have to add something like this. It should work now. Okay. Yeah, that's pretty dumb. So our tests are still working. Fine. Cool. So now we get this error message. We can remove our debug print here. So we just see undeclared variable C. I think that's pretty cool. Now scoping seems to work. Next thing that we could do is we could add like Boolean literals like true and false. So I guess let's do that. But before that, I'll have to take a little break because I have to pee. Lol. So see you soon. I'm back. Let's get this party started. Okay, so where were we? I think we were about to add Boolean literals, right? So, first step, lexer. We need a new token kind, keywords true and false. Add them here. So right, true, false. Dum dum dum. Cool. I mean, we have to lex them here. True and false. Nice. And now we'll have to pass them as expressions, I guess. Do we? Huh. How do we do that? Do we? I don't even think that we need to add. Like, do we need to add new expression type? Like Boolean literal? I guess we do. Yeah, I think we do. Okay. So let's add a new expression type. Okay, we have to split this file up like right now. This is way too big. Jesus. Boolean. AC Boolean expression. Abstract AC Boolean expression. Up value. Token. Cool. And now parse primary expression. No, parser. Parse primary expression. We just say, okay, if we have token kind true or token kind false, just say boolean with token kind and or we can just also pass the token here, right? Just token clone, create associate function. Let's undo that. Let's just say and boolean. We'll just take a token. Yeah, okay. I'll take the value as well. It's fine. That value. Cool. Now we're parsing Boolean expressions. We'll have to add that to our visitor. Visit Boolean expression. Nice one. Add it to the printer. Sub that keyword. Nice one. Oh, did not want to do that. Visit our Boolean expression. We just say, I guess, okay, if that works, it's cool. So now we can run stuff. It's gonna say if true. Resolver. We don't really care about Boolean expressions, I guess. No resolver. Actually, yeah, let's not say this is a keyword. Like add Boolean value or Boolean literal. It's gonna say like const Boolean color light magenta. I think would be cool. So we just say and add Boolean. It's not used anymore because we say the Boolean literal, add Boolean. Cool. And in our visitor, we have to implement this as well. Boolean value. Cool. So this is not, wait, what? It's not different from magenta. Yeah, interesting. Then let's okay. Yellow is fine, I guess. If true. Cool. And let's see if that works. We just have to remove C. It does. Okay. And if we say false, B should be -1, right? Nice one. Okay, cool. So next step, I think it's time to like write some tests, right? Yeah. Let's write some tests. So first we'll ensure that everything is still parsed correctly. And how can we do that? We'll say, okay. Tests, but it should parse if statement. And that does not work. Like if true, then we just say like 20. What? Where did you come from? Here we're just gonna say that a is equal to 1. A is gonna be 20 in here. If a is greater than 2, or not greater than 0. A is equal to 30. Okay, so what do we expect? So we expect if, and we expect, first of all, we expect that statement, a number, cool. And we expect if, we expect binary variable, expect 0. We then expect, what do we expect? We expect block. We expect less stable with a number 20, no, not binary, it's number 20. Then we expect test is, you know, else. We expect another block statement, another that. Okay, so we'll have to create block, I guess. C verifier. Okay. Visit block statement. The assignment expression. Yeah, so it's not gonna be in a statement. Assignment, actually. It's just assignment, so we were wrong on here, I guess, because this is not let. It's just assignment. Do we have an expression statement? We don't. Okay. Okay. So maybe this will actually run. Does. Okay. That's pretty cool. Now we have a working test for our if statement. Parse if statement with else. Check test. Parse if statement. Is that correct? Like let number if binary. Yep. Okay, cool. And I guess we could add some diagnostic tests. Should report. Okay, as we already do that, so that's fine. And should not report any errors when shadowing. What? Okay. So it just says let A be A. So simple examples, A is equal to 0. And then we'll just say, okay, cool, that A is equal to 10. And we should not get any errors here. And that is correct. And that is cool. Nice one. So I guess the next step would be to add a while statement. So what do we want to achieve? Maybe something like that A is equal to 10 and while is A greater than 0. We'll just say A is equal to A minus 1. And at the end one of A. So this should return 0, right? See? Okay, undeclared variable while. This does make sense, kind of. It's actually funny because see how the AST is parsed. Just like variable, binary expression, block statement, variable expression. So, first step, add a while token count. Second step, add, or okay, let's just smooth this stuff because now we could actually move all this stuff here, like AST visitor, I guess. So we'll just move that to visitor. That's fine. And probably move this to a separate printer file. Okay, that's cool. String. So stuff is user. Okay, visitor is private. Wait, didn't, what? For AST printer, no, that's wrong. You have to go back to the printer. Okay, that's funny. I don't know how that could happen. Can we just like import the whole struct? Something like this. Does that work? Okay, cool. It works. Did not know that. That's nice. Okay. Nice. Now everything works again. And we have a little bit smaller file. Okay. Where are you? Okay, nice. Tests are still running. Our tests. Nice one. So now our file is only like 500 lines, which is okay. So we'll have to add a new statement here. Statement kind, while. CY statement, abstract, CY statement, while keyword, yeah, condition, and body, which is gonna be a statement. So in our parser, we say parse statement. If there is a while token, we will parse a while statement. Parse while statement. And while statement. Cool. So this we now have to add to our visitor like this statement, and we'll just add a method called visit while statement help. Cool. What? So this does not work very well. How's this parsed? What the actual? Okay, we're kind of missing like a line break here, which is weird. Okay. Yeah, we'll look into that. But first of all, we'll have to add a while here. So I'm gonna say visit while statement. So a keyword, white space, expression, white space, body. Cool. So now we should print it properly. Yeah, okay, that looks good. Now we have to add it to our evaluator. So we're just gonna say while expression. Yep, exactly. Now we 0. Nice. And that's how we've now added a while statement. That actually was pretty fast, I guess. So what we can do now is we can write some tests for while statements. And after that, I honestly don't even know what would make sense to implement next. I mean, we could try and start implementing functions. I guess that would be cool. Because functions are actually like kind of complicated because you have to look out for a lot of stuff. Or what else can we do? I mean, I think function calls would make sense. I think they really would. Yeah, let's do function calls then. After we've written some tests, of course. So, I see structure tests. It should parse while statement. Well, yeah. Okay, cool. Wow. And we have to add some methods to our visitor. If we have to visit our while statement. And now our test should run as well, right? Nice one. Okay, so we've tested this. Next up, do we really want to do function calls? And we really could. We really could like add functions. Do we want to do that? I think we do. I guess it's really time for function calls then. Yep. Okay. I'll put that into a separate video though, I think. Because this video is already too long, I suppose. So, quick. So YouTube, I see you in the next video, stream. Just stay here, please.